Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. My name is Mohammed Fathala from the XCG Group, and it's my pleasure to introduce David Abramson from Monash University. He'll be talking about high-throughput, low-impedance e-science on Microsoft Azure.
Okay, thanks, Mohammed. So it's a fairly audacious title. I'll try and explain what we're talking about. I do realise this is the graveyard shift, right? So thank you for staying, and we'll try and keep you awake. My colleagues and I will do our best at that, won't we? But perhaps I thought I might start with something that would keep you awake, and has absolutely very little to do with the talk, but does impress upon you that I do have some knowledge of Windows. These are in fact the stained glass windows that I make, which have nothing to do with computing at all. So if you want to get away from cloud computing, then I recommend this activity, because there's almost no computing involved. However, what I want to do is go through and talk about a tool chain that we've been working on for quite a few years, actually. And we've been through multiple generations of infrastructure. So I'll just start out with some motivations, looking at different applications. I'll tell you a little bit about the tool chain, and then something about what we're doing currently in mapping this onto Azure. So the message of this little part of the talk is that when you get the tools right, magic happens. And I hope I can impress that upon you. So let me just quickly walk through a few different applications that use the infrastructure we've been building. This is a case study we did with a colleague in geography who had a really simple question to ask. The question was, can burning the savanna, the northern grasslands and tree structures of Australia, affect the climate? Really simple to state that question. Of course, totally impossible to do the real experiment. You're not going to go out there and burn the savanna to see what happens. Even if you do go and burn the savanna, you've got to do it 50 times so that you get some statistical significance. And then, clearly that's not the sort of experiment you can do. So this is something that we did in silico. We launched lots and lots of climate models, ensembles of climate models, and ran them on global infrastructure. The little graph on the bottom right shows the number of processes we're using globally. And what you can't see on the scale is that that's actually 6 months of computation in real time, of lapse time. So we tied up a lot of machines for a lot of time to answer this question. If you're interested in the answer, perhaps ask me in the break and I'll tell you whether burning the savanna can in fact affect the climate. But the reason that you might think it could, when you look at this picture at the bottom, is that you can see that the energy profile, the surface energy budget's totally changed. And so because the physics changes, you might imagine that you can in fact affect climate. So that's science that was impossible. We work with a number of colleagues who are trying to model biological systems in some very fine detail across a huge range of parameters. And so the order of magnitude shift in scales here is something like 10 to the 11 to 10 to the 15 difference between modelling perhaps at the molecular level and modelling up at the organ level. So they develop complex models, and then they want to know, because they're so heavily parameterized, whether in what parameters you in fact need to fit to the model to make it do anything reasonable. So the cartoon on the top right is the characterization of a single ventricular myocyte in the cardiac system, a single cardiac cell. And this is what we think goes on inside the cell. There are ions flowing in and out, and so they draw cartoons that describe that. There are mathematical equations that help describe it, and there are parameters to those mathematical equations that are very difficult to estimate. You can't measure them, and so you have a nasty inverse problem of knowing what a real cell does, what a simulated cell does, and you want to adjust the parameters so they do the same thing. And so this is another one where you have a new way of thinking about the problem, but you want automation, you want computation to underpin things. Here's another example about new ways of thinking. This is a project we're doing with Leica Microsystems. Leica Microsystems make microscopes. The microscopes look like the one on the top left here. And they're standalone instruments. What they've realized is that these need to now be integrated into a much larger fabric of computers, of storage devices, of display devices, and that these can be, in fact, physically distributed. So the little video on the top right there, which is designed to keep you awake in this last session, is in fact a video of a demonstration we did of this to our colleagues in Germany, in which we were controlling microscopes in Australia and Germany, taking the data, processing it, shipping it around the globe, and displaying it on display devices. Now, when you get the tools right, I'm just going to slip through that slide. When you get the tools right, you find that the same tools can be used for radically different problems. So this problem now is one in electrochemistry, and it came about by a discussion with one of our other collaborators when we were working on the cardiac models, who spoke to a chemist friend of his and said, I think these tools could actually solve some problems you have in electrochemistry. So the same generic tools we've managed to apply from the environmental one I showed you initially in the burning of the savannah, through microscopy, through to right through to electrochemistry. It's the same generic tools. So let me tell you a little bit about the tool family, because the tool family now is something we've been building over the last many years. It's a tool called Nimrod. There are many varieties or flavors of this, and it serves what sounds like a very simple problem. The problem is that I want to explore what happens when I run a computational model, changing some things. So it's what some people call parameter sweeps, and the tasks involved are execute this model and change the parameters. That sounds really simple, but when you do that on complex infrastructure, it gets much harder. So we produced a version many years ago called Nimrod-G that runs over the grid and allows you to specify two very simple things. Here are the parameters, here's how you run my code, go and do the experiment. And it will distribute that work over computational resources and pull the results back. Sometimes those experiments get too large, and sometimes then you don't really want to look at the whole state space. You want to look at, you want to actually try and optimize some output. So Nimrod-O is a version that allows you to measure the output of a model. It might be some metric, some objective cost function, and you want to say things like, tell me the parameters that minimize this metric or maximize this metric. So there we apply nonlinear optimization techniques to guide the search through the search space. There's another version called Nimrod-E that executes a thing called design of experiments. You may have heard of this. It's again another technique for pruning down the amount of work you do by not looking at all combinations of the parameters. So you're not necessarily looking at the higher order combinations. There's another version called Nimrod-K that executes scientific workflows. And you've heard a little bit about workflows at this talk, at this conference in a couple of the sessions. So we have many different varieties of this, and you can see that we can keep going for at least another 22 versions, which should see me through to retirement, and still keep the name of the project. This is the overall ecosystem of three of the tools, Nimrod-O, E, and G, and how they interact. And really, the message here is that the user comes along with a very simple description of their problem. So we've put a lot of effort into making this simple for people to do what they do best. And so we're working with scientists, and their work is doing science. So they write what's called a plan file. A plan file is a very simple declarative description of the problem. You don't have to read all of that, but that is a real experiment. So it gives you the scale of it. It says, here are the parameters, here's how you run my code, go away and do the work. And what happens is they log into a portal. Nimrod-G looks after the process of generating the data sets. It looks after the problem of distributing those to computational resources, and I'll come to this in a moment. And it pulls the results back again, and these are often collapsed in some way. Nimrod-O actually talks to Nimrod-G, so it's the one that does the nonlinear optimization. It generates jobs, sends them to a lower layer, and they're executed. Nimrod-E likewise generates jobs and sends those to the lower layers. So it's a hierarchical structure. Down at the very bottom, we have some level of middleware. Traditionally, that's been grid middleware. Now, as we move into the cloud, we're starting to explore cloud systems there. So the cycle that a user goes through is generating jobs, And you can see down the bottom here, the different colours show you coloured to show where they're running. So these jobs are actually executing in multiple places. They're sent to a network of machines. Results come back. And the important thing is, from a scientist's perspective, what they see is often a very condensed or visualised set of results. Users interact through a portal. I won't go through the details. You've all seen portals. But it displays things that they need to know about what's going on in the experiment. There's another version of Nimrod called Nimrod-K that actually sits outside this ecosystem at the current time because it's a new version that executes scientific workflows. The reason it's called Nimrod-K is the K stands for a system called Kepler. There was a little bit of discussion in one of the other sessions before about, why didn't we use this workflow engine or that workflow engine? Well, there are so many workflow engines. It's like the old joke about standards. You can always find one which will do what you want. We happen to have a very good working relationship with the people who build it. It's an open source project. And so we've integrated a lot of the other ideas from Nimrod into this hybrid Kepler-Nimrod system. And so one of the things we've added is massive parallelism. And so we can create quite large experiments that scale up and scale down elastically, if you like, as the work flows through the workflow. And so users now can write experiments not using the declarative plan file, but using a graphical editor. And this shows a MATLAB model running in the middle here that's running across a parameter sweep. So we're driving parameters into the MATLAB code and then graphing the results. The graph down the bottom, in fact, shows the number of processes we're using on a cluster to do that experiment. So that one gets up to sort of like about 500 processes at a time. When you put optimization into the workflows, something really interesting happens is instead of taking an acyclic graph, which is what most people represent a workflow as, we put a cycle in it, and that allows you to do search. So if you think about generating data sets and looking at values in space and then evaluating them and then bringing that back around and then looking at some more, that's a logical way to do it. And so you can write these optimization workflows inside Nimrod OK it's called, and it allows you to cycle around multiple times. So you can mix and match things in some pretty flexible ways. Okay, so that's the tool chain. The question is, what have we been doing over the years? Well, really, I've been working in high-performance distributed computing for a long time, and really what's changed underneath us is the fabric all the time keeps changing. The scientists still want to do the same things. So we started out quite a few years ago building a version of Nimrod that only worked on clusters. We actually spun out a company. There's a company still around in California called Accellion that produced a commercial version of this, and it runs on clusters or small collections of machines. Nimrod interacts with other queue schedulers. So it will drop jobs into the queue manager depending on which queue manager happens to be running on that platform. That's very effective. We got into grids in the 90s when people started to realize that you could distribute this stuff across the globe. And this gave us our first real taste of wide area elastic computing. And so instead of being locked into one particular cluster, I can expand it out and run on multiple resources. We provided that portal that I showed you before as a point of presence. So independent of location of the computational resources, I can launch those experiments globally. And we introduced really two ideas there into the grid that no one else was talking about at the time. One of them was this whole idea of charging for time. Now, the reason we introduced it was not so that you'd make money out of this infrastructure, but so that two users who had conflicting deadlines could reason about them. So if I need this work done by tomorrow and you need the work done by tomorrow, and we have no way of saying who's more important, then they'll just compete and no one will meet a deadline. So we introduced the idea of a computational economy to try and allow you to trade that. So I can say, I need this done by tomorrow and I'm prepared to spend this much. And that was a really interesting idea, but there was no infrastructure out there to support it. So just hold that idea for a moment. The second one was that we'd worked with lots of grid systems, and they're a pain in the neck for distributing applications. So if I've got a code and it needs to run on 30 different sorts of machines, we could easily spend as much time as it took to run the experiment setting the experiment up, getting the code installed, testing it, and all of the like. And the problem is the heterogeneity. So I had another PhD student working on the idea of virtualizing the environment so that it became more homogeneous. So just hang on to that idea for a moment too, and I think you'll see that both of those have translated very nicely into where we are with clouds. At the time, we leveraged grid middleware. We did a lot of work with the Globus guys. We had a port of Nimrod for Legion, plus various other ad hoc standards. So when we go into the cloud, some things get easier. Well, it's no great surprise. Clouds are really all about centralization and homogeneity. The grid was almost the exact opposite of that. So centralization, of course, is much easier. Running Nimrod on one cluster was always much easier. And plus these observations that virtualization is a really good idea to make deployment simpler. So build once, run anywhere is a really good model. I don't want to be logging into 30 different machines trying to make something work. And now for the first time, we've got a computational economy for real. Amazon or Microsoft are very happy to take my credit card and say, we will give you this many resources, you see if you can meet the deadline. So I can say things like, I need this finished Monday morning, or here's my credit card, do this as quickly and cheaply as you can. We've been mixing and matching these because we've got the infrastructure in place to do this. So I can cloud burst so that I can say do this much on my local infrastructure, but if you find you need to go to a remote machine, then do that, and I'll show you an example of that. So our first experiment integration was to try and take this into IaaS. So like everybody, we've done an EC2 port of it. And really, it's a question of changing the device called the actuator. The actuator is a component of code in Nimrod that knows how to start things on a remote resource. So we keep the grid middleware stuff in place, so we can still talk to grids, but we've built actuators that go to other platforms. So the cloud actuator for EC2 is one that knows how to start stuff up on EC2. Now guess what the de facto middleware is for talking to IaaS clouds? Well, it's SSH. Right, the lowest common denominator is I know I can get something running by doing SSH. I'm not sure that's a particularly powerful interface, but it's the one that's available. So we've got some stuff that launches code on EC2. Nimrod's generic architecture I didn't really talk about before is that what we do is we send things called agents out to these remote resources and they come back. They come back and ask for work. Let me just skip over that. So we can do this cloud bursting, and this, you can see the green, yes. So this is a plot of jobs in time of a real experiment we did between our local cluster and an EC2. And the green line is in fact the EC2, and the red line is our local cluster. And what we said is, we want you to finish this experiment by 660 minutes. And the scheduler worked out fairly early on, well, it started by using our local cluster, worked out that it was no way it was going to make that deadline with the computational resources it had available, so it scheduled some stuff on EC2, and so you can see it bursting here up to an additional 150 nodes or cores running. Part of the way through the run, the scheduler worked out that it didn't have to send any more jobs to the EC2 in order to make the deadline. Now, if it had changed later on, it would have spawned up some more. And so it actually came in here and landed pretty close to the deadline. So what we're doing at the moment is working on an Azure implementation. This is a little bit trickier. Some of these things have been discussed yesterday and today. But for a start, PWAS has much more variety and, of course, by definition, is a higher level. So just look at Azure versus App Engine. These are really two quite different environments. Mostly, you'd say that the PWAS environments, and in fact, the way Amazon's used is for doing web app hosting. Nimrod's much more generic than that. We want to run an arbitrary code on a machine out there. And so the way that PWAS providers allow you to run things is by giving very tightly sandboxed code. So for example, restricting it to Python or Java or whatever and keeping them in a sandbox. That's way too restrictive for Nimrod that wants to start arbitrary computations. So we've started working on an early port of this. It's really just to put our foot in the water and see how much of it we can get going. So we're not trying to port Nimrod, the core of Nimrod, to Azure. We're just porting the thing that does the work, which is called the agent. That's the device that I spin out. and we're building an actuator that knows how to start stuff up on Azure. And so this works something like this. It's currently being constructed. So user comes along with a Nimrod experiment and starts that. And then what we do is we actually ship the agent code out to Blobstore. Now the agent itself is a Python program. So the stack is pretty messy. It's Python running on Cygwin, all frozen up and sent out to run on a Windows environment. So the first thing we do is we ship it out to the Blobstore so it's actually available. And packaging that up. The other thing we do is we create a queue which is used for getting the parameters from the actuator out to the actual instances of the agent. So what happens the next stage down is that we send these agent parameters out to the queue. So there are going to be as many agents running as there are as we want instances of computations. And so we put in the queue unique identifiers for each of those. We spin up a set of workers using the worker role and pull the agent from Blobstore and pull the parameters from the queue. So the first thing the agent does is come up and read something from the queue to find out its identity. And then using the standard stuff that's already in there, the agent contacts back to Nimrod and starts pulling jobs. This is the same sort of glide-in structure that Condor uses. You have to do it this way on whether it's clouds or grids or anything. You have to do it this way to reduce the latency of getting things started. Even under the grid middleware, it was simply not effective to throw stuff into the queues that were out there running things. So that's our current architecture, and we've sort of got bits of this built. So I can't show it, can't do a demo today, I can't show it to you working, but we are starting to get bits of this working. I started out with applications. We've actually got some time on the Azure resources, courtesy of Microsoft. And so our intention is to run another couple of application drivers, but these ones are a little bit different from the ones I showed you initially. The first one is a volcanic ash dispersion code developed in Costa Rica. This is pretty topical. This is code that computes the trajectory of volcanic ash and tells you where it's going to land. This is a problem in Costa Rica, as it is in Iceland, just knowing where the stuff's going to finish up. So we did the graphs I showed you before were in fact EC2 graphs running of this initial version of the code. We're building a version at the moment that'll run on Azure, which is a later version of that. So that's a nice heavy piece of computational science. The second one is one where we only have Windows binaries. It's a simulation of the electricity grid, and it involves a group at University of Queensland who are actually looking at placement and mix of different sorts of generation strategies. So mixing green energy with traditional energy sources and then trying to decide how much to produce and where to produce it. And again, that simulation is actually a Windows-only package, so it's perfect for this environment. Okay, so I just want to acknowledge the people who do the work. The people who do the work are down the left. The people who give us money are on the right. Certainly want to acknowledge Microsoft, who's given us money from time to time. Always welcome, although US dollars aren't worth too much anymore, I might say. And I'm 2 minutes early, so happy to take questions.
Hi, nice talk. I really like the scheduler that organised the cloud bursting, so it just grabbed enough EC2 nodes to make sure that you finished by the deadline that you'd set. I was wondering, there must be some assumptions that makes about the time that the jobs take, and whether in the early stages of the computation, the scheduler looks to see whether the time for the jobs is variable or constant, and acts accordingly.
Yeah, so thanks, Paul. So we've always done something really simple, which is just take the average time. So if there's a lot of variation, it's going to get that wrong. But if you've got enough jobs, it seems to work quite well to do something really simple-minded. So we just do a projection based on how long they're taking on average. There's plenty of room for more complicated things, but that seems to work a lot of the time.
To clarify on the previous question, why did it decide, the scheduler decide at the end to stop working on the local cluster and go into the cloud completely? Because it seems like you could save money by doing some combinations.
No, it did actually stop using the cloud. So the peak that went up to, if I can find it, the peak that went up to 150 was the cloud. The green stuff is EC2. The red stuff is our local cluster. Now, there's a lot of detail that I haven't talked about there, and there's a lot of research problems that we haven't solved. And one of them is just that's solving when to send work there, but the whole issue of when you spin up machines and then shut them down again, we haven't solved that yet. So that's a hard problem.
Any other questions? Okay.
No.
Thank you very much, David.
Thanks very much. Get an extra 5 minutes, Shantenu.
Am I out of uniform? Yes. I wish you guys had told me.
Can I have you take your name tag off for me? Sure.
Not forget who it is.
Identity crisis, as long as Dave doesn't see mine.
When I go upstairs, I'll bring his image up on the screen and you might go live.
Is there a pointer? No. He's not no. No. Okay. I'd like to present Shantenu from Rutgers University. He's going to be presenting abstractions for life science applications on clouds.
Thank you. So first of all, thank you very much to the organizers for the invitation to talk at the Cloud Futures workshop. This is work done with a series of members of my group, but in particular with Andrea Luckow, who actually works for BMW. So here's a quick overview of my talk. But in a nutshell, I'll try to put everything over the next 30 seconds. I come here talking about cloud futures, and before I wax prophetical about what we're going to do, I want to tell you that our experience over the past 10 years in developing honest-to-goodness, scalable, distributed applications is what's going to guide a lot of our judgment and a lot of our work in the cloud space. We've worked on production cyber infrastructure like the TerraGrid, the UK eScience national grid infrastructure, so on and so forth. And we've learned some things. We've learned things that work, and we've learned a lot of things that don't work. So seeing something like Azure, we're exceptionally heartened to see that many of these lessons have either been explicitly or implicitly learned. And a lot of the abstractions, a lot of the missing features that these cyber distributed infrastructure did not have over the past years have been provided almost as a first class, almost as a priori consideration. That's great. But what I'd like to present to you is that, whereas that's a great first step, given the scale of problems upon us, that is not enough. More needs to be done. And that is the central hypothesis of my presentation, that we need some more, we need these abstractions, and we need an interplay of the system level and the application level abstractions in order to really do the science at scale that we would like. So the formal structure of my talk is I'm going to just go through maybe what is really a 2-hour lecture in maybe 5 minutes of just try to give you some bullet points of the lessons that a decade of honest-to-goodness developing distributed applications has taught us. The one take-home message I will try to leave you with in these 5 minutes, more an article of faith than something I'll be able to postulate, is that there is a unique role for abstractions for distributed dynamic applications. And I will come back and I'll try to present some more on what I mean by dynamic. But then moving into the present, I want to try to spend a few minutes by exploring and developing a couple of applications, a compute-intensive, a data-intensive application, try to tease out the primary characteristics, the common basic characteristics of these applications, and try to lay out for you what the challenges of life sciences applications, generalizing from 2 to infinite number of them, on the clouds are. And again, along the theme of the first point, I will try to present to you one very simple abstraction for dynamic distributed execution, and that is that of a autonomic, intelligent pilot job. But then I'm going to dig deep into the details of something that we've actually engineered and solved on Azure, and that is what I call the Replica-Exchange simulations. Compare some of the pain points there, some of the advantages of Azure over using something like TerraGrid. And then, again, the take-home message I want you to learn, which I've already mentioned, is that Azure addresses many of the pain points that traditional distributed infrastructures have not. But there's some interesting lessons to be learned by doing this on the TerraGrid, which I hope to communicate to the Azure members in crowd. Then I will end by, again, this is the part where I wax prophetical, where I don't necessarily have a lot of data, but I'm going to try to show you how building the right abstractions can help us build the right services. And I propose building a next-generation sequencing and analytics service on the Azure, very similar to what we're doing on NSF's XD and TerraGrid. Okay, so very quickly, let me just try to tell you that the lessons, the primary lessons that we've learned. So first of all, the space of distributed applications, as no surprise, is very large. But the number of effective and extensible distributed applications is small. And it's important to appreciate that distributed applications is more than just submitting a job here and there. It's a complex interplay of a large number of different reasons why you want to break a large problem up into smaller problems. You decompose them, you spread them out, you may do this for a large number of reasons, and then you want to bring them back in together. So it's not just this embarrassingly parallel set of n tasks where if you've seen one electron or one job, you've seen them all, right? So it's more than that. The second point is developing distributed applications which can utilize these broad range of environments, execution environments, and to actually coordinate across these resources is genuinely a hard undertaking. And I'm going to try to break this up into an intrinsic and an extrinsic set of factors, right? And one interesting lesson that personally I've seen over the past 10 years is that the community has been shying away from having distribution as a first-class, again, attribute of their applications. They've done everything possible to run away from it. I postulate, and hopefully we'll be able to discuss this, that that's no longer a possibility, that's no longer going to work. And let me just get into this intrinsic and extrinsic description. So the intrinsic reasons why developing distributed applications is hard is that you're now trying to coordinate and manage, control and coordinate over multiple heterogeneous distributed sites. And so in order to do this coordination across a large number of resources, which you must in order to have the whole greater than the individual sum of the parts, you need the right capabilities. And often these are not provided. Or managing them, even if they are provided, managing them can be quite difficult. Additionally, unlike, let's say, parallel applications where you have a well-defined design point, high performance, peak performance rather, you have many different attributes that you might be trying to optimize or design it for when you're developing distributed applications. And so, again, there's a wide range of distributed application models, I would argue, larger than the range of parallel applications. And then there are the extrinsic factors, that is, the infrastructure upon which we execute, upon which we take our development applications. And this is an entire different can of worms as to the heterogeneity, the level of sophistication, the software complexity, reliability, robustness, so on and so forth, is highly variable. And you have to develop your complex development application development task on what is essentially has been a fickle back-end infrastructure. Okay, so again, I've kind of alluded to this, but what I just really want you to remember is that thinking distributed is now more and more important because you just, in some cases, cannot localize all the data, and you have to fundamentally accept that you have to work with the data in a distributed context, right? If nothing else, that's just one simple ground zero case, right? And therefore, we now start needing programming models that provide this distributed, that accept this distributed computation going to the data, and dynamically determining how and when this data compute should go to the data, as again as an important requirement, right? So this is mostly the past of where what has happened and where we are right now. Now let me introduce clouds into the mix, and I think Dave gave a nice kind of his model of cloud, so I will not proffer my model of a cloud, but I'll just say clouds, as I think we'll all agree, address several of the barriers that we've encountered, namely just two, which I think will be uncontentious and we'll all agree. They provide a better control over the software environment, either through virtualization or through other things, but more control and, if you will, better predictability. And also this illusion of unlimited and immediate availability of resources, important keyword being illusion, can lead to better capacity planning and scheduling. Right? But if there are advantages, if there are some clear barriers that are overcome, there are some barriers that are not overcome. And these are, for example, in the fact that we still don't have any way of a priori managing the distribution, either the logical or the physical distribution of the tasks that the distributed applications have, right? And so, in a nutshell, clouds present a natural and a positive evolution, but again, we need some more care before we say that clouds are going to help us, are going to be the panacea for distributed applications. So this is where I changed tracks after having taken about 10 minutes to give you a background to try to talk to you about two applications. The first is this Replica-Exchange. And so, by the way, please hold on to these thoughts that I've laid out for the distributed applications, and then I'll come back to that in a while. And I guess I should have switched my wireless off. Okay, so the first application that I want to talk to you about is this really Replica-Exchange, which is something used by about 300 to 400 biological physical papers every year to study everything from distributed application, drug discovery, to just trying to understand protein conformation, so on and so forth. And really what this application is, you start off with n different ensembles, very similar, but maybe a couple of small parameters like temperatures are distinct. You let them run for a while, and then you find a partner, and then you exchange with a partner. You just change the temperature. So it's really not zero coupling, but a very loose amount of coupling. So you do need some kind of coordination. And if an exchange is accepted, you do some changes. If an exchange is not accepted, you then carry on. Right? So you can see first and foremost that this is not your trivial parameter sweep. So something like Cirrus, which is a kind of a capability provided by Azure, does not work here. Right? And I just want to point out that there are many, many different variations of the Replica-Exchange algorithm. So again, the second application I want to talk to you about, and luckily I don't need to say much because you've seen variations of this slide about next generation sequencing, and the major challenges that this poses is that of analytics. But what I do want to do is to give you a specific example of a next generation sequencing analytics application. And I will proffer BFAST, just one of the many, maybe a dozen existing analytics applications. right? And there are reasons why, because I think this is rich in many ways, richer than many others. In addition to the fact that it has higher sensitivity, it's just important to realize that there's 3 kinds of data sets involved here. The short reads, which is the actual data coming from the machines. Then there's the reference data, which is, let's say in this case, the entire human genome reference. And then there's index data, which is one of the kind of pre-processing that has been done so that now the alignments can be done more effectively, right? BFAST has several sophisticated capabilities. It can be used in a multi-threaded mode. There's this option in which you can do a trade-off between memory and the time to completion, so on and so forth. The point I really want you to take on here is that there are all these different configurations that BFAST can be used in. And essentially, this maps into a trade-off between computation versus memory versus I/O versus degree of distribution. And this comes about from the fact that you can chunk the read data, the short read data, into smaller bits. And you can start off, therefore, with concurrent tasks. But the concurrent tasks might end up having on the same machine. But the concurrent tasks might impose an I/O bottleneck. And therefore, you might start considering distributing it if you can, in a way, move the data, the reference data around in advance. So you start seeing the cascading of opportunities and possibilities to get the right kind of sweet spot, right? OK, so here's going to be 3 different examples of real. By the way, I just want to tell you that I work with honest-to-goodness biologists, honest-to-goodness applications. So this is not Mickey Mouse toy problems, but these are real data sets that we're working with. And for the purpose of this talk, I'm just going to focus on this column and this column, and just leave you that the full human genome is beyond the capacity of any of the infrastructures, including XD and its largest machines, for us to handle. Okay? So just eyeball these numbers, keep them in mind. We're really talking about single problems, gigabytes, hundreds of gigabytes. OK, so again, this is a long data presenting data to say really that in this application scenario, you really have this ability to do trade-offs between the computation, memory, I/O, and degrees of distribution. And really just trying to run this through very quickly is you can chunk the read file sizes, and as a consequence have more concurrent data tasks, beg your pardon, or you can change the number of threads, and therefore each task can operate at a different level of, if you will, fine level parallelism. Or you can kind of vary these two together. And I just want to tell you that once you start doing that, you start running on a single machine, you start running into highly, at times, unpredictable behavior, because at one stage, you're memory bound, and at some other stage, you're I/O bound. And again, not enough time to work through all the details, right? So from the 2 applications, the Replica-Exchange and this next-generation sequencing, I'm now going to have the ambitious task of generalizing for all life science applications on clouds. And what are the challenges? Well, you'll appreciate these 2 at least, the characteristics. You'll appreciate that in general, distributed applications have these characteristics or challenges, the where, when, and how to distribute. What I now want to tell you is that as a consequence of things like cloud bursting that's been referred to several times, and kind of the localization, the different models of localization, you now have all of these challenges, along with the fact that these have to be determined dynamically, as in runtime. Because you're not really going to know in advance what the right sweet spot is, because you don't know which kind of back-end system, so on and so forth, you're going to use. So really what we need is the ability to support heterogeneous, distributed, and dynamic workloads. Jeffrey raised a very good question yesterday. I don't know if this was in public or on the way back. What is the kind of infrastructure? Is there a single infrastructure for such NGS analytics? And contrast this with communities like astronomy and high-energy physics that have converged on a single infrastructure. No such infrastructure, cloud infrastructure configuration has been agreed upon. And Jeffrey also mentioned that the TeraGrid is not used for data-intensive applications. And building this infrastructure is not trivial. And so that led me to think, so why? Why is this the case? And obviously, I'm going to come back to this later as to what the challenges of building the infrastructure for all of this are. But I just want to separate the fact that there are hard bits to this problem, and there are practical bits to this problem. And some of you know I've been working on the SAGA project for the past 3 to 4 years. It provides the very basic abstractions which you need to develop distributed applications, so the primary distributed functionality. And lots of details here, but what I want you to focus on in the past 6 to 8 months is that it's now essentially a community standard. It's the official access layer to at least the 2 largest grids in the world, the European grid infrastructure. 2 months ago, I was signing a memorandum of understanding with EGI. And recently, if some of you saw Ian Foster's and Andrew Grimshaw's presentation yesterday, SAGA is kind of the official access layer to the NSF-XD's architecture, right? So what I'm trying to tell you is that through these basic community standard basic primitives, you can now start building capabilities that, whether they're standards or not, or that's not the point, they are abstractions based. And what I want to show you here is, other than try to give you an overview of SAGA, is that you can start building higher level capability from these primitive distributed functionality, namely that of a pilot job, which really is nothing but a container for dynamic task placement in it, inside this larger container, right? And in the SAGA world, we call this BigJob. But thanks to the fact that you now have a well-defined API, you can define a higher level API, that of a pilot job, and through this building up of layers and stacks, you now have a single API that works as a pilot job across these 4 or 5 different backends. And we've done this, right? Okay, I won't show you data. So the question that begs to be asked is, what is unique about a pilot job that is built using the right abstractions? Well, you can now make this an intelligent and autonomic pilot job, and you can start doing sophisticated things like application level scheduling and other advanced capabilities, like having pilot jobs as well as pilot data, as in bring the pilot capability to the data world and not just the job world, right? And so again, what I'm trying to convey to you is the basic capability of an abstractions-based approach, a layered abstractions-based approach to distributed application development and deployment, right? So again, I changed tracks here, and I'm just going to run through very quickly the kind of honest-to-goodness example of how this capability that I showed you has been used on Azure to try to handle a very large number of Replica-Exchange problems. And again, maybe I should just run you through that. We use the basic primitives and abstractions that Azure provides. So we use the worker roles to we use a BigJob, as in a pilot job, to kind of run over a worker role, individual worker roles. We use the affinity support to place the workers, to place the tasks on specific worker roles. And we use the blob service for our storage. We use the table storage and the queuing system for our messaging between the replicas. And we've gone through the whole kind of engineering to make sure that this is essentially robust, so we don't have replica failures. And here's my take-home message, in the sense that we now have Azure provides the ability to really run a large number of replicas effectively. And as you can see, the lines are essentially flat with an increasing number of replicas, which really tells you that the coordination costs are well controlled, as the number of replicas that you run increase, the coordination cost does not go up. So all kudos to the AQS, so on and so forth. Okay, but the point I want to make is this just is a starting step. We've now done what I think, and I have not been corrected in the past 6 months, the world's largest Replica-Exchange simulations on the TeraGrid. The difference being this has taken maybe 2 orders of magnitude more sweat, blood, and tears than it did on Azure, and also the fact that we didn't have the time and the access to doing a Replica-Exchange of the scale that we've done on the TeraGrid. So here's 256 replicas, each replica 32 cores, so do the maths, approximately 8,000 cores being marshaled. Okay, and now once we have the basic infrastructure in place on the TeraGrid, we can start doing experiments with different algorithms, coordination algorithms. And for the first time ever, we start seeing that this is your vanilla Replica-Exchange, but by introducing certain different kinds of coordination in the exchange phase, you can start getting really impressive improvements in performance. So almost a first attempt that we would like to do, and I come here with a request, is to enable us to start doing Replica-Exchange on Azure at the scale, to start seeing, given the effective coordination cost, what's really an infrastructure coordination as opposed to an intrinsic algorithmic advantage. We don't have the ability to discern that so easily here. Okay? Not to mention that, again, as I told you, this is used by 300 to 400 papers every year to study everything from protein structures to drug discovery, so on and so forth. Okay, very quickly, I have about 3 to 5 minutes left, so I should just really run up and say, so now coming on to the second problem, that of the analytics of next generation sequencing, we now start proposing gateways, again with the final intent of trying to provide this as a community service. And this is where, again, the SAGA-based abstractions come in. But now we have not just only pilot jobs, but also extensions of pilot jobs to provide these pilot capabilities integrated with the pilot jobs. So a very complex set of numbers here, and I could spend half an hour just telling you about this, but what I want to tell you is that this capability, which we call a DARE-based gateway, has been used to submit jobs to Ranger, which is the TAC machine, 65,000 cores, Queen Bee, which is Louisiana's flagship machine, Ranger and Queen Bee together, and future grid machines, and I just saw Jeffrey leaving, time to completion TTC, and various different configurations, right? So what I want you to see is that really this is meant to be, Ranger is meant to be at least at least twice, if not 4 times as more powerful than Queen Bee, if nothing else, is 3 to 4 years younger as a machine. But you can see that for exactly the same configuration, the number of nodes here is 16, and this is, each node has 16 cores, this has 8 cores. There's a bizarre performance difference. And again, this is the kind of the I/O boundedness that I was referring to. First thing. The second thing is that when you run on Ranger and Queen Bee, the coordination costs, here, lead you to, although high, still lead you to somewhere in between these two numbers. And thirdly, I just want to point out that you can start dynamically determining how to decompose your tasks, whether to use a combination of grids, clouds, so on and so forth, depending upon what is easy for your data distribution. Okay? And again, this is for one kind of data set size. You can increase the problem set size here for larger and larger, and the entire kind of space, the sweet spot changes. So you have to kind of dynamically recalculate. Okay? So just wanted to now rush through the fact that, and this is where I'm waxing prophetical, that we now want to integrate this pilot data and pilot job capability and try to see how we can improve some of the numbers that we have here, and obviously have some kind of autonomic decision-making capability of how to do the distribution, right? So which helps support this dynamic execution that we need to manage. Okay, so this is just trying to tell you that it's not just advanced capabilities like NGS, but even the most primitive MapReduce style applications can benefit from these abstractions, and benefits everything from providing a simple infrastructure-independent scheduler to fault tolerance, to also more, if you will, heterogeneous workloads, so where your initial data size is not, let's say, chunked into uniform bits. So you can manage all of this, obviously in the distributed context, that's where the power comes out, of MapReduce using these capabilities. And again, I don't have data here because this part of it is still trying to, we're trying to get out and get some basic understanding. So, as I said, we brought all of this, and even if you ignore the pilot store part of it, and you just focus on the infrastructure-independent pilot job, we are standing up, literally as we speak, a capability, NGS Analytics as a service, on NSF's XD. And there are a whole list of challenges that we still have to worry about. Everything from the right choice of the algorithms, tools, based upon the input data set size. Everything from appropriate task scheduling placement. And we need to start learning about how the high-energy physics community has kind of aggregated themselves to really worry about not individual workers' throughput, but the community throughput. And there are lessons learned when you stand this up as a service. Obviously, distributed data management, efficient data transfer. We heard some great data and some analysis from Tefik yesterday. So we need to start learning all of that. Ultimately, we have to get to the optimal point for every different application, every different data set that is being analyzed. Right? And there's no reason why this capability that we're working on the XD cannot be done precisely for Azure and stand this up as a service. Obviously, this cannot be done for human genome, as we've discussed several times over the past couple of days. But for all other non-human genome requirements, this is clearly a community service that we could consider standing up. And it's not just NGS analytics, but the drug discovery and other examples using exactly the same framework and approach. Okay, so wrapping up in the last 30 seconds, you've seen that life sciences applications provide this nice mix between data intensive and compute intensive, and especially at scale, there's some very interesting challenges. I've hopefully conveyed to you that the best solutions are those where there's a nice interplay between the abstractions provided by the system, for example, AQS, and application level or development runtime user-defined abstractions, right? And through that, we've shown some relative ease of implementations of the Replica-Exchange pattern, just one, that relied on efficient and scalable messaging. And we pointed out that the overall effect was the same as that of the TeraGrid. And really looking forward, what we need is a combination of take this approach, extend this to handle dynamic data, and things like affinity that Azure provides, finer-grained affinity and data compute affinity. We're in the position to start exploiting these capabilities and then providing them as hooks to the application and really trying to start doing analytics and other kinds of efficient life science applications in ways that we have not been able to do earlier. I'll end with the acknowledgements. And just want to say some of this work was done on Azure, some of this work was done on FutureGrid, and I've benefited greatly, obviously, from members of my team, but also private discussions with Jeffrey and John Weissman. Thank you very much.
Shantenu. Do you have any questions? We have time for one question for the next speaker. So I have a question. In the abstractions aspect, when you talked about the abstractions that SAGA provided, can you elaborate a little bit about the programming abstractions, if there are any, that are provided to the people building the applications? Is it for containing the applications, distributing them, and hiding that from the application developers? Or do you extend some of those abstractions to the actual application developer?
So what was the last statement? Or do you
expose some of those abstractions to the actual application developer?
So the abstractions exposed are really file transfer, job submission, replica management, and some communication with whatever the backend service will be. So the semantics are and the syntax is kind of, if you will, uniform, and then you write these adapters which translate it to whatever the backend system is.
I see. Do you foresee the need, or is there are there plans in the pipeline for concurrency control, perhaps, or consensus?
Yes. Yes. Yeah, and those would be out of bound. You could implement any of these out of bound of SAGA. SAGA just gives you the very basic distributed functionality and none of these other abstractions.
Thank you. Let's thank our speaker again.
Great, that can go in pocket. Here is the clippers that advancing the back. If you want to, you can also use the arrow keys up and down, left and right.
Good, thank you.
I will go upstairs, put that on the screen or what?
Is this C3L? Or is this
That's the name of the, I'll define that. It's the name of the lab.
Oh, C3L. Okay.
Our final speaker for today is Craig Mudge from University of Adelaide, and he's going to talk about the parallelization of geoscience apps at C3L with Azure.
C3L is the name we've given to a brand new lab, a collaborative cloud computing lab. So the outline I'm going to follow is talk about a no machines lab, which is what we've built. A method, a geophysics method, a relatively new one for imaging subsurface, and it's called magnetotelluric, which I will define. Then talk cleaning and processing the data, which currently, before we moved to the cloud, was taking the geophysicists 4 to 5 weeks per run to do the inversion runs using their desktops. Look a little more in detail on the results, and then talk about future work. So the reason we came to do this new lab is that I had been spending some time on a national working group in Australia looking at the opportunities and barriers for cloud computing, believing that this was a terribly important new technology. David Abramson, who spoke to you earlier this afternoon, was on that working group, as was Gordon Bell, a couple of people from IBM and Google, as well as some other university chaps. And then early last year I decided I really want to do some real work in the cloud instead of analyzing it and talking about it. And the University of Adelaide provided a home. And so that's how we started. We managed to get, early last year we had some seed funding from the local state agency, the Department of Mines, rather like your the American USGS in Menlo Park, the Geological Survey branch, and also a Microsoft Jim Gray seed grant. And that was tremendously helpful in terms of the amount of money and an amount of guidance that we had from colleagues here. It's no machines, even our source code control system, which is SVN, that is in the cloud too. So we make no use of the university infrastructure. You're only allowed to have laptops and netbooks in the place. We started last year about June, and we have 1.5 people since then. This no machines is a bit weird for a person like me. I used to be a computer designer of some machines like VAX in Boston, then some chips, floating point processor, a fast Fourier transform chip, and then at Xerox PARC sort of building some very high performance routers. And now I've confined myself to saying no hardware, no machines. But of course the architecture I'm interested in now is the warehouse-sized data center. So yes, we still have some wonderful architectural interesting things. Magnetotellurics, or MT for short, uses the magnetic and electric fields of the Earth to determine the resistivity structure underneath. So there are some natural sources of electrical and magnetic radiation that come from lightning at the equator, from sunspots. These are things that are occurring all of the time, and the Earth reacts with telluric currents to these happenings. And we're using this, then we decided that it was not just for minerals, and there you see 50 kilometers deep underneath a very large dam, very large minerals mine, but also, and I'll talk a bit about geothermal, and also looking down here, storing CO2 in depleted gas fields. So we're building it with our geophysicists as a platform technology. So it measures the electrical resistivity of what's underneath it. Now, the MT can go 10 kilometres, 100 kilometres deep, unlike seismic, which only goes about 2 kilometres. But seismic has a much better resolution. So there you can see that different geologies have different resistivities, or different conductivities. So igneous rocks, and then over at the left, with good conductance, a saline water plus heat. A graphite, the source of a lot of minerals, is over there with good conductivity. Now, the methods there are different electromagnetic methods. We're using the one in the dotted rectangle there, magnetotellurics. But if you use ground penetrating radar, also is used to image under the surface, and but that only goes down, a matter of tens of meters. Now look at the frequencies that are involved. Clearly, with high frequency, you can only go down a small amount. With low frequencies, you can go right down towards the inner core. So with magnetotellurics, the frequencies, note the frequencies there, from about 10 hertz to 10 to the minus 3 hertz. So the period are seconds and minutes and so on. Even that English, almost that English measure, fortnight. The MT, the signals are random in nature. The excitation is random and very, very weak, and it requires substantial processing. So that is why we find it an interesting area to work in. The reason, when we set up the lab, believing in e-science enabled by cloud computing, we wanted to choose, we had two choices of application, because the two areas where the state of South Australia, where Adelaide is, the two areas in which we are world-class, one is wine and the other is minerals and energy exploration. We chose the second. So this is one of our geophysicists out logging in the field. This is about a 10-hour drive north of Adelaide. And so he has been, that's him in last month. They're now using our cloud-based code to run the processing now. The instrument there is a diagram of the instrument, which collects 5 things over a time series. The electrical characteristic over a period of a day, the magnetic are collected there. And you can see, Stefan, there are about 4 people up there. Here they're actually they're imaging underground for the hot rocks, and I'll talk a bit more about that. But this gives you a sense of what the field work is like. The interesting thing is that in MT, it's only a few gigabytes of data are collected over a few days. So it's not a big data problem yet. So it's very much a computation. You can see the cables going out there above this cable. Stefan is sort of sitting on the cable. It's underneath his chair. And that's running. They go out to about 50 meters in the north direction, east direction, and then the flux plate measurer is just in the center. The processing, you end up with a 3-dimensional image at the right hand of my slide there. But the processing initially consists of cleaning the data, cleaning that time series of data. So there's 3 stages. The time series is cleaned, is converted into a representation of apparent resistivity, which are the impedance tensors, and then you go into the forward modeling and inversion to produce the image. So the first task of, let's say there's about 50 stations that you would have logged over 5 days, then they can be processed in parallel, but that's not a very, very hard task. It's only just a couple of hours each. But the forward modelling and the inversion, being an inversion problem, that takes about 4 weeks. The geophysicists and geologists do not use the local supercomputers or the national supercomputers because, in their words, they're too hard to use. They'd much rather use their laptops and... Therefore, of course, they have to worry about provenance of the data and so on and so forth. But anyhow, this is an overview of the processing. The code-enabled burp. There is a robust statistical algorithm implemented from Chave at Woods Hole. It's a program they've been using. Our guys have been using for years. It gets rid of the outliers. You know, if you haven't buried the cable properly, a kangaroo can come along and sort of root it up. Or there might be, we look for 50 hertz signals that somebody has started a generator. But there's not a lot of human activity around these places of interest. But these two, so the outliers are removed, and then we go into the once we've got the impedance tensors, go into the inversion. So that is a result there. That is a visualization of a large area about 25 kilometres across, and about 40 kilometres across, about 20 kilometres deep, and underneath what's called the Gawler Craton, which is the Gawler Craton is the major crustal zone in South Australia. It holds a lot of iron oxide, copper, gold, and a lot of uranium. And you can see this deep area of conductivity, right? So that's low resistivity, okay, high conductivity right there in the center. So that's an indication, and that's going down about 20 kilometers. So that's an indication of some interesting potential minerals there, and it's in the northwest-southeast direction. That's the way it's going along. If anybody's interested in geology of this, send me an email. I've got all of the appropriate papers that our colleagues, our geophysicist colleagues, have written. By the way, we are at the major international conference on geology and geophysics. The international one is at the end of June this year, and our geophysicists are presenting our the cloud results there. The processing, it turns out that and remember we took big chunks of Fortran code and didn't do a thing to them. We just changed, I'll talk a bit more about that in a minute. It turns out that the processing for the frequencies are independent, so you can put the different frequencies across different machines. And we do that there for the sensitivity matrix computation, forward misfit. They use the word misfit to talk about the error, and the smoothness function. The notion in the modelling is you take a guess on what the geology looks like. You use Maxwell's equations to generate what the electrical and magnetic response is to that bit of geology, and compare that with what you'd measured in the field. And you keep on iterating on that. It iterates according to some optimization algorithm, and currently the guys are using a nonlinear conjugate gradient method. The results there, you can see how the speed up gets better with frequency. I've plotted here the time in days against frequency, and these are so the simplest case with just 5 frequencies, it's 12 days versus 3.9, and the geophysicists are most interested in a large number of frequencies. So this is what we're getting right now. We're running on Amazon, and we are moving into onto Azure. That's the structure we have for Amazon. we've put as much effort into the web application, almost as much effort into that as into parallelizing the Fortran code, because the geophysicists, we want them to interact with the web application, not with some damn computer program. And that's what we see there. Now, the diagram, the equivalent under Azure, is still a work in progress. Frankly, we're only about a week away from being able to draw that accurately, but we haven't. That's happening right now. A couple of numbers on the reconstruction of the code. Code was written in the sequential version was written in Fortran 77. It's 22,000 lines. And clearly, we went through looking at to find the computational blocks that are amenable to easy parallelization. That we found that there's independence on frequency. Separated the control logic from the actual numerical work, and then that control logic and optimization is handled by a Python script. There's about 500 lines of the Python script. Let me now talk about, so we're actually moving, we're now almost at Azure. We've got various things that we've packaged and run and so on. We're almost to the point of being able to do our first 3-day run on Azure. Let me shift gears and talk a little bit about another interesting area, which is in geothermal. Geothermal energy, heat under the ground, heat under your feet. When we think of Yellowstone or of New Zealand, it's sort of geysers and hot steam is coming up. This is very different. Enhanced geothermal is where you have granite rocks about 5 kilometers underneath the earth, and they're sitting there at about 200 degrees C. And the idea is that you will, having located those, that you'll put an input well, the blue one's an input well going down. It runs through the granite rocks and goes up the surface in the red line and drives the hot water drives and steam drives an electricity generator. 95% of the investment in this type of geothermal is in this state of South Australia. And this region here I've shown here. So that's where the Parallana hot rocks are. It's in the middle of nowhere. However, that huge Olympic Dam site is over yonder, about 200 kilometres away, and that needs electricity. And so there's a possibility that the power will be supplied for part of that. So by the end of next year, the first stages of of a 5 megawatt power station will be underway. But the science we're working with our geophysicist friends is a before and after. So in April, the guys were up logging data before there was any fracturing of the hot rocks. So they're building the image now of what it looks like without any water flowing through. The fracturing of the rocks occurs next month by forcing water down here, and then we will then do the imaging in the after situation, and it should look, and the resistivity of saline water will show a much higher conductivity in that area. So that's the before and after that's going on right now. And all of this processing is being done in the cloud now. Not the 1 day's worth of the outliers, but the multiple days is. In a little bit into the future, it turns out there's a wonderful organization called Geoscientists Without Borders. And they have done a pro bono, they've funded, a couple of our geoscientists are members of this Geoscientists Without Borders, and they've gone way up north to work with this community of Aborigines in the Nipabana community, because they're to image the aquifers, the source of their water supply. So that's a real-life groundwater understanding that's going on. A second one is that our geophysicists have been invited, this is just last week, invited to go over to Western Australia, where there's a different sort of geothermal. which is sort of heat close to the ground. I don't understand the engineering all that well yet, but one builds heat exchangers out of this proximity heat and sort of cools houses and heats things. But one of my favorite projects is the Square Kilometre Array, a radio telescope. And that will have a huge computer centre near Perth. And so the possibility is that this deep heat will be used to power the computer centre near Perth that does the processing of the Square Kilometre Array data. Some future areas. I want to get a satellite link, and a portable satellite transmitter, and put that out in the field so that the outliers can be, that processing for the outliers can be done remotely, going into the cloud, using historical data to enhance the data that we're gathering in the field. Secondly, we'll just go into some improvements of the current Fortran program. Thirdly, look at a genetic algorithm, an alternative to the current optimization. And then joint inversion is an interesting approach where you use two different methods and different methods of imaging. Here's an example of a part of South Australia where it happened. There was a very good understanding of what the subsurface looked like. So this experiment with MT was, the sounding with MT was done, and then using that plus a seismic jointly together produced an image which is much closer to the real thing. So we want to do a lot more of that, and that will all be done on Azure, running this inversion in production. Word. We want to make our modelling available through the Geology Survey to explorers all around the world. Explorers sit in China, in Canada, in Brazil, looking at the data that the government agencies provide. We want to bring that from static into dynamic and provide modelling on demand, and with the modelling being done in the cloud. So that's and we look like Microsoft has agreed to join with us in a Australian Research Council grant application in that one. Quickly to finish, I got set on the right course by Ed Lazaska in this e-science area. Just so I'm a simple computer designer, and he helped set me on the right course. We've had some very good help from colleagues within Microsoft Research, Gordon Bell, Dennis Gannon, Catherine Van Ingen, and John Warren. And of course, the real effort is our collaborators. Graham Heinsohn, standing there out in the Flinders Ranges. He's the geophysicist. He's the geophysicist collaborating with us, believing that cloud computing is a step forward in computation. So he's the guy. Pinaki is the person we employed on the Jim Gray Seed Grant, part-time Wei Wang, and Stefan is another geophysicist. This is a national facility, so we're working with some top people. So I've talked a little bit about a no machines lab, the magnetic telluric method. Our future work is, that's when we'll be able to come back to you with some, saying, look, here's the problems we had on debugging. These are the costs associated with getting the data up there, and so on and so forth. At the moment, we have that just for Amazon. So thank you, and I'll be glad to take some questions.
Questions?
Yeah.
Everybody eager to be done? Dennis, you look like you have a question. I'll give you my mic.
So in working with the EC2 work that you've done,
yeah.
What has been your experience with moving the data back and forth?
Because there is such little data, we put it on EBS, and that's that. Okay.
So it's not an issue.
And that's not an issue. That's not an issue. All right.
Question over there.
The data issue is when we've got the intermediate is going to become worse when we get lots of intermediate data, huge stuff that we've generated within a computation.
Just to clarify, why did you say that seismic waves go only to 2 kilometers? Because we, in our department, they're processing seismic waves, they go, well, I mean, active seismic waves, they go all the way to the Mocha surface, which is like 40, 50 kilometers. And the actives from the big earthquake, they also penetrate very deep.
By seismic, I meant the seismic exploration that's used by petroleum companies and oil and gas, where you actually have a controlled source. You either thump the ground or you explode and measure the reflection off there.
They go all the way. They reflect from the Mocha surface 40 kilometers down.
Okay, well then we can chat about this offline, but my understanding is that it's you need to go to another method as soon as you want to go past a couple of kilometers, as you do in geothermal. Okay.
More questions? Okay, thank you very much, Craig. Let's thank our speaker.